Okay, let's get started. So a couple of announcements, as always. There's homework 6, which is due Tuesday, and project 4 will be due next Friday. So just keep an eye out for those. So today we're going to kind of extend our discussion that we started last time about adding actions back to the picture, right? The point of artificial intelligence is that we want to make smart decisions, right? And so we added these actions back to our sort of classic Bayes net diagram, and we started, putting little A's on things, and then now we can make decisions, and we talked about what decision networks look like. So here's a decision network. This was the one that we saw last time. This is the one where we have an umbrella. We're trying to decide if we should bring it with us. Well, what factors might we be interested in if we're going to think about bringing our umbrella with us? The weather seems relevant, so the weather is part of this model. The forecast is something that we can use to get information about what the weather is going to be. That also seems relevant. And then the point of all this is that we're maximizing utilities. We're utility maximizers. We want to come up with the outcome of future events that is going to be the one that maximizes our expected utility. So if we bring our umbrella with us to the beach and it's a sunny day, we might be sad because then we can't, play catch with our friends because we have to carry this umbrella around with us, and so we're sad. But if we don't bring the umbrella and it's sunny, and we can go to the beach and we can have a fun time. Meanwhile, if it's raining and we don't bring our umbrella, we're going to get wet. That's going to make us sad. And if we do bring our umbrella, then we're super happy because we like carrying umbrellas in the rain. Okay, so we have utilities associated with each of these outcomes, and we're trying to do the expected utility maximization thing because that's what we love to do. And we're trying to think, what's the best decision that we can make? What's the best action, this umbrella action, that we can take that's going to maximize our expected utility? Okay, so this is all just recap from last time. Okay, so maximum expected utility, this is like a concept we've seen a bunch of times in this class. We're seeing it again here, but hopefully it shouldn't come as any surprise to you. It's like we just want to do the thing that causes the most utility. And in this case, now that we're connecting actions to Bayes nets, we have the ability to do the thing that maximizes our utility, conditioned on the evidence of what we've observed so far. So this is what the picture looks like. And now we're just adding actions to our Bayes nets. So actions take the form of these sort of square or rectangle nodes. So umbrella is an action. It means we can bring our umbrella or we cannot bring our umbrella. We have weather nodes, which are like chance nodes in a sort of game tree. So that's why they have circles on them. In Bayes nets, they just all had circles on them because it's just like that's how Bayes nets are. But think about it in terms of a game tree, and it's like, oh, that's kind of like an expectation node. That's like an interesting connection there. So we now have actions. We have expected utilities. So that's the diamond nodes, the ones with U on them, and so those are affected by actions, and they're affected by chance nodes. So all of these concepts are kind of coming together. We have Bayes nets. We have actions, we have utilities, we have sort of game tree-esque things. And so with these Bayes nets and actions together, we can now calculate the actions that lead to expected utility maximization. Okay? So we have, I mentioned these different kinds of nodes. We have chance nodes now. We have parents on chance nodes, but actions do not have parents. So actions, we just decide we're going to take our umbrella, we decide we're going to leave our umbrella, and we're using this model to inform our action selection decisions. But it's not like there is something in the model that is influencing our decisions. So there's this interesting distinction here. Like, of course our behavior is going to be dependent on what we see in our model, but the model itself doesn't have this connection back to the action. The action has no parents in this diagram. Was there a question? So here with the umbrella and weather, can the utility only take 2 values? And your question was 0 and 1, maybe? Yeah, so utility in general is just a number. It's something that we assign as value of various outcomes. So this is like just a real number. And we now have to think about like, okay, well, if the real number can be any real number, but like we're assigning a real number to outcomes. So the utility node is going to have some number of outcomes associated with it, and the number of outcomes will be associated with How many types of weather could we see? And how many actions can we take with our umbrella action? So we're going to need, if you're thinking about like what's the size of this table, right? Think of this as like it's a Bayes net, right? What's the size of this table here for the U variable, right? So we're going to have a weather column. We're going to have well, it's kind of annoying that there's an umbrella column. This U is the umbrella. And then we can call this V, okay? So the value or the utility of this decision node is going to have an entry for each one of these possible outcomes, right? So if we see that let's say that there's rain and we brought our umbrella, yes. If there's rain and we didn't bring our umbrella, if there's sun and we have our umbrella, sun and we didn't have our umbrella. So we have a value associated with each one of those outcomes, and those are the outcomes here. So there's 4 outcomes. So this table has 4 values in it, and each one of them is a real number. How much do we like that outcome?
So is sun with no umbrella the same utility as rain with umbrella?
Sun with no umbrella or rain with an umbrella? I see. So matching your umbrella to the situation, does that mean that you always prefer it? No. So maybe umbrellas are heavy and you don't like carrying an umbrella, right? So even if you are perfectly matched to the situation, you might prefer still when it's sunny and no umbrella. I mean, I think I prefer when it's sunny and there's no umbrella to having an umbrella even when it's raining. Like, I have different utilities for each of these outcomes, yeah. Yes? Okay. Yeah, great question. So the question is, again, like, why doesn't the umbrella node have parents? So we have to keep our 2 hats separate. One is we're the model designers, and one is we're the people who are using the model. Okay. So when we're designing this model, we're saying I'm gonna design a model that has umbrella in this action node. And when we're designing the model, we're saying the user can choose their actions independently of all these other variables if they so choose, right? So in that sense, like, it doesn't need to have parents because their actions can be made independently of the rest of the nodes in the Bayes net. And if they can make their actions independently, then we want to model it this way. But then when you're using the model, when you're the person who's saying, okay, I want to choose the expected utility maximizing action, well, now you're going to be looking at your network and you're going to say, okay, well, for each of these actions, what's my expected utility? Can I maximize that somehow? Maybe I'll use the information that's contained in this decision network to do that. It means that, like, in some sense, your action is going to depend on whatever it is that you calculate with this thing. But now we're wearing the model user hat, not the model designer hat. Thanks. Other questions? Okay, great. So we've added these different types of nodes to our network, right? We have chance nodes, we have action nodes, we have utility nodes. And our goal is the same as it's always been. We want to maximize our expected utility. So recapping from last time, the way that we're going to do that is, let's suppose that we get some evidence. We're going to instantiate that evidence. We're going to select the action nodes each possible way. So umbrella or no umbrella. Let's say that, like, my forecast says that it's going to rain, right? It's going to be bad weather. Then I think, okay, well, in the bad weather scenario, if I bring my umbrella, how does that turn out? In the bad weather forecast scenario, if I don't bring my umbrella, how does that turn out? So I think about this particular evidence variable, and I think about all the possible actions. That's the first 2 steps. Then we calculate the posterior. This is like, how do we get the distribution over possible utilities given all the evidence? So otherwise this works exactly like a normal Bayes net. We calculate the expected utility for each action, and then at the end, we just choose the action that maximizes that expected utility. Right? So we looked at this example last time. We have the umbrella weather forecast network. We see that the forecast says it's bad weather. So we think about the 2 different actions that we could take. We could leave our umbrella or we could take our umbrella. Each one of those is going to be a different setting of this umbrella variable. And you can see that this table for utilities has 4 distinct values in it, right? So we care about these values exactly this much. I don't know why those are our preferences. Maybe you can think about whether those are reasonable preferences or not. And we have our sort of Bayes net table. So conditioned on weather, we have these probabilities of the forecast being bad. So these are useful conditional probabilities that we're going to need to do this calculation. And so what do? Well, we say that the expected utility of leaving our umbrella behind when we see that the forecast is bad is, well, we're going to sum over all the probabilities of weather given that we had a bad forecast. And these come from our Bayes net. We can calculate them with Bayes nets. And then we multiply by the utility of leaving our umbrella behind and seeing that that was the weather. So for each of the possible outcomes, we get its utility from our utility table. We multiply by the probability of that outcome based on our Bayes net, and then we sum those things together. And so we can do that for this example. We get 34. Okay, so these numbers are coming from this table, and these numbers are coming from this table. Making sense? Yes. Bad represents that the weather forecast says that we're going to have bad weather. Sure. The forecast is rain, but that doesn't mean that there will be rain. It just means that the forecast said it was going to rain. Okay? So we do all this for the umbrella left behind case, and then we keep going. And we do the same thing for the taking the umbrella with us case, right? So we do all the same probability math. We add these things together. The probabilities are coming from the same table, right? 0.34, 0.66, both coming from here. But now our utilities are for the other outcomes, the ones where we take the umbrella, right? So 70 and 20. So we add these things together. We do the weighted sum. We get our 53 points. And so we say, all right, taking the umbrella gets me more points when the forecast says bad weather than leaving my umbrella behind. And so if we're doing the expected utility maximization thing, we say, all right, well, that's a better action. It's going to bring more expected utility. I'm going to take my umbrella with me. I don't know if it's going to rain. I just know the forecast said it's bad. But I'm going to take my umbrella anyway because I think that's going to be maximizing my expected utility. Okay? So the optimal decision is to take. The maximum expected utility, given that the forecast is bad, is whatever the utility is for taking the best action. So in this case, it's just the maximum of 34 and 53, and so it's 53. So this concept of MEU, we haven't written it this way before, but it's the same thing we've always seen. So maximum expected utility, that's just taking a max over these two expected utilities. Okay. So then we talked about the value of information, the value of perfect information. And so we said, let's suppose that I want to know, should I bother to check the forecast? Right? So how much value is there for me in going to check the forecast versus if I don't check the forecast, right? So you have to always compare this. What am I comparing the value of checking the forecast with? Not checking the forecast. So either I know what the forecast is or I don't, and I'm comparing the value of those two different scenarios. And you say, okay, well, what's the value of one of those scenarios? Well, we're expected utility maximizers. So it's the maximum expected utility for either of those scenarios. If I don't know the forecast, I'm going to do maximum expected utility. If I do know the forecast, I'm still going to do maximum expected utility. So it's just how much does knowing this information, whatever it is, help me to maximize my expected utility. So it's like someone has this forecast in a box, and they're saying, would you like me to open this box? They're not telling me what the forecast is going to be. They have no control over what the forecast is going to be. All we can do is decide whether to open the box. Okay? So we can open the box or we cannot open the box, and we want to know what's the value of opening this box. Right? So we can calculate our maximum expected utility with no evidence. With no evidence, we did this one last class, so I'm not going to go through the math again. We get 70. We just did this. So if the forecast is bad, we can compute the maximum expected utility. We did this on the last slide, so this is 53. So I won't take you through the math again. We can do the same thing if the forecast is good. The forecast might be good. Who knows? We get the maximum expected utility is 95. Okay? So each time we're instantiating the evidence, we're thinking about all the actions we could take, we're computing the expected value or the expected utility of taking that action, and then we're taking the action that leads to the biggest expected utility. So now we want to say, what's the value of knowing the forecast? Well, the forecast could be good or it could be bad. I don't know. I mean, what are the probabilities of it being good? What are the probabilities of it being bad? Well, we can actually just ask our Bayesnet for these probabilities, right? We have some forecast distribution. It depends on the weather. We have some prior over the weather. So we can actually compute this table. And I'm not going to go through how to do this, but this is like the sort of normal Bayesnet stuff that we would have done before. So we can compute this marginal distribution over the forecast. We see that it's going to be good weather 59% of the time and bad weather 41% of the time. And now that we know these numbers, we can say, okay, well, there's two possible forecasts. If I decide whether or not I want to open this box, well, I have to think about those two possible forecasts that I might see. And I'm going to see them in these probabilities, so I have to take this weighted sum. Right? So my maximum expected utility of opening the box, of seeing the forecast, is 59% times 95. That's 59% times the forecast being good. And 41% times the forecast being bad. And in each case, I'm doing the maximum expected utility thing underneath. So if I want to know the value of seeing the forecast, the value of seeing the forecast is I'm getting this maximum expected utility over the expectation of these two different outcomes. Like, what's the chance that I get good forecast when I open the box? Well, we look at our Bayesnet, we see the probability of good forecast, we multiply by the maximum expected utility. And then we do the same thing for the bad forecast. So this is the maximum expected utility under the forecast distribution. And we see that it's 77.8. And if you were thinking about this from before, we saw that with no evidence, right, it was 70. So we can subtract one from the other, and we see that when I take this new information, I get this forecast, I open the box, then I see that I gain 7.8 units of utility. I don't know what units we would measure this in, but maybe it's dollars. Maybe we get $7.8 for our effort. Maybe we're just 7.8 small amounts happier about this day, right? So 7.8 utility has been extracted from basically knowing the information that's contained in the forecast. Doesn't tell us whether the forecast is good or whether the forecast is bad, but we know that if we open the box and see which one it is, that will net us 7.8 units of utility. Okay? So that's the value of perfect information, yeah. Correct, yes. Those numbers are the chances of the forecast being good or bad. Those are things that we can calculate. Normal Bayesnet rules apply here. So we have a weather prior, we have a conditional distribution over forecast given weather. We can invert this with Bayes' rule and all the sort of math we did with Bayesnets, and we get a marginal over the forecast distribution. And that's just all I've put in this table here. Yes, question?
Is this value of information a constant, or does it depend on what other information you have?
Is the value of information a constant, or does it depend on other information that we have? So what other information do you mean?
Like if there were more variables, like a different type of forecast.
Yeah. Yeah.
The value of this forecast.
Okay, so in this very simple scenario, there's not a whole lot of other information we could have, but we could know what the weather is, right? We could have listened to the forecast or not listened to the forecast after knowing what the weather is, right? So if we knew the weather, what's the value of learning the forecast? Not much, right? Because we already know the weather. So the weather, in the same way that Bayesnets work, sort of isolates this information from this information. I don't know why my laser pointer isn't working anymore, but it isolates this information from this information. So once we condition on knowing the weather, we don't really need to know the forecast anymore. So the value of learning the forecast conditioned on knowing the weather is not the same as the value of knowing the forecast conditioned on knowing nothing else. Does that answer the question? Thanks for that. Other questions? Yeah.
What extra information is the forecast telling us?
What extra information is the forecast telling us? Well, it's telling us something about what the weather might be in general, right? If we don't know the weather already, then the forecast is giving us an indication of because the weather is somewhat correlated with the forecast. Usually the forecast is not perfect, but it's more reliable than no forecast, right? So the value contained in the forecast is some information about the weather, but not, so we have perfect information about the forecast, but we don't have perfect information about the weather. So this perfect up here, this value of perfect information is saying, I perfectly know all the evidence variables, but I don't know everything else. Okay? Yeah.
So would we assume that the weather is the current weather and then the forecast is about the future? So that in the example of like when you're saying that you're leaving your umbrella into the sun, that's the weather at the time, but not when you go out and actually use the umbrella?
I think it's a little weird. So the question was which weather are we talking about? Is it the current weather? Is it the future weather? When does the forecast get made and with respect to which weather? So it's a good question. I think that the way that we're modeling it here is that we're talking about the weather later today, and we're talking about the forecast of that same weather later today. So it's a little backwards because in some sense, this forecast is actually dependent on what the weather has been doing for the last 10 days or something, and certainly for the last day. And so that's going to be helpful in predicting what the weather is going to be in the future. This is a simple model. You could try and make it a more complicated model with a hidden Markov model if you wanted to. You've observed the weather for the last 5 hours, and so you've seen what it was. You don't know what the underlying conditions are. You don't know where they're going. You can't necessarily predict perfectly where the weather is going to be later today. But you could use a more complicated model and maybe get a better prediction. Yeah. More questions, yeah. Yeah, so we could essentially, so you're saying, what if we look out the window and see what the weather is? Right, so let's say that let me clear this diagram out. Let's say that this weather is later today's weather when I'm either playing with my friends at the beach or I'm sitting in the rain with no umbrella. That's the weather we're talking about. And you're saying, well, what we could do is look outside. Well, when I look outside, that's a different piece of evidence. It's saying that right now, the weather looks like it's sunny. So that tells me that later today, it's likely to be sunny, but I don't know, right? So yeah, we could add other evidence variables to our model, and then we could think about looking outside. Yes, we can do that. Other questions? Okay, great. So the value of information of knowing a particular capital E evidence variable conditioned on having some other information, which is the lowercase evidence variable. We just did this. I mean, it's just the math version of the same thing, right? So on the left side, we have one expression. On the right side, we have the maximum expected utility had we not even looked at the evidence. Okay, so without opening the box, that's the term on the right. And then if we do open the box, remember we have to think about all the things that could be inside this box. We say, yeah, and just remember, this is the box. We think, okay, what's inside this box? Well, maybe the forecast is good. Maybe the forecast is bad. So now we're summing over all the possible forecasts. And I'm just going to draw it in a different color, right? So we're summing over all the possible forecasts because those things could be what's inside this box. And then we're multiplying by the probability of that forecast. That's coming from here. Of the maximum expected utility for that forecast. And so that's coming from here. And then we're subtracting this value. That's coming from here. So all this is doing is writing down the process for what we just did in math. This is saying the value of perfect information of this capital E is to do this and subtract off the value of no information. Okay, more notation stuff. I think I'll skip that. So here's the other example that we looked at last time. It was this idea of drilling for oil. And we said, okay, there's two locations that we could drill there's location A and there's location B, right? We don't know which one of these has oil, but we can drill in one location or the other. It's expensive to drill. We can only drill in one of these locations. So we got to pick A or B. That's this action up here. That's the drill location, right? Whether we get utility depends on where we drill, but it also depends on where the oil is, right? The oil is down here. It's in location B, but we don't know that. So the oil location here also influences our utility. And we can choose whether or not we want to go out and purchase this scouting report from some shady vendor who claims to know where the oil is. And we can decide, how much is it worth it to ask this shady person where the oil is? And how do they know where the oil is anyway, right? So we can think about this scouting report and say, is it really worth getting this scouting information? And so we can build ourselves a decision network. We can ask ourselves, what's the value of perfect information if we were to obtain this scouting report? And the numbers in this table will tell us what the value of perfect information is. It'll tell us, well, if we could just know where the oil was, what would be the value of perfect information, right? And these are not necessarily the same thing. One is the scouting report. This is like getting the forecast. And one is the oil location. This is like knowing what the weather is going to be. Two different things. One is information about an observation, and one is information about like the ground truth variable that like is influencing our utility. Does this distinction make sense? So when we talk about the value of perfect information, we're getting perfect information about the scouting report, but it's not the same thing as knowing where the oil is. It's just knowing what the scouting report is. Okay? All right, I'm not going to go into the details too much here, because we just did one. So you could ask about the value of imperfect information, but in this class, we don't really have any such thing as imperfect information. We just have perfect information about sort of observations that tell us about other variables. So this is like the scouting report. So no such thing as imperfect information. The information corresponds to observing one of these nodes. That's our evidence. If we observe the scouting report, we have perfect information about the scouting report. That means we might have like some uncertainty about what the actual oil location is. We might still be slightly uncertain what the weather is going to be later today, even if we do listen to the forecast. So in that sense, it's a little bit imperfect, but we have perfect information about the thing we're observing. If we listen to the radio, we know what the forecast is. If we go and get the scouting report, we know what the scouting report says. So it's perfect information about that. The rest of the stuff is sort of just noise in the way that the probabilities work out. Okay? Questions on this? Okay. So that's the introduction to like how can we add actions to these probabilistic models. And today we're going to talk about another model called a Markov decision process that adds even more stuff to these models and helps us make even better decisions. Right? So imagine that I'm this robot and I'm trying to get this gem because I really like gems. They're very expensive. They're very shiny. This one's blue. That happens to be my favorite color. And so we're on this ledge and we don't know what's going to happen, right? Anything could happen. I could maybe safely make it to this gem and be happy, or I could fall off into this pit of fire and die a horrible death. So like the probabilities are important here because we don't know what's going to happen. We want to model the uncertainty of the world. We have these actions. We just added actions to our probability models in the decision networks part. Now we're going to say that there's searching for like the best sequences of actions and the best strategies for making decisions. And we're also going to add a time component as well. So this is saying I have an action decision now, and I not only want to take the action that leads to good immediate rewards, but I want to take the action that sets me up for success in the future. Like, how did I even get on this crazy ledge? Like, maybe I should have just walked around and like come at this thing from the other side. Maybe that would have been a safer play. Like, so now we're thinking about strategic decision making, long-term search behaviors, and so we're trying to add all these different pieces together. So actions, search, probabilities, time, we're going to combine all that into one model. Okay? So we need to have like a motivating example. All of our sort of different units have had these motivating examples. The one that we'll use here is a grid world. This is not the only kind of Markov decision process, but it's a useful kind. This is like think of like a Pac-Man maze kind of thing, grid world situation, right? So we have an agent, they sit in this grid world, and they have to exist in one of these squares. Okay? They live in there, and walls block the agent's path, so they can't walk through walls. And they can take certain actions. So we'll put the actions in there. And in this particular grid world, just for the sake of making things interesting, the actions are noisy, okay? So this is like sometimes you're not that good of a robot, so when you try and go forwards, you kind of move to the side instead with some low probability, okay? So 80% of the time you go straight forwards when you're trying to go forwards, and then 10% of the time you go left, and 10% of the time you go right. Okay, this is just like the way we've designed this particular grid world. You guys can all go off and design your own grid worlds if you like. This is our grid world. We're going to stick with this for a bit. So there's some probability that your agent can slip and move to the side instead of moving forwards. Notice that like this is maybe kind of weird. In this grid world, they never slip backwards. So that's fine. That's just part of our grid world. So you can design your grid worlds however you like. We've designed it this way. And the agent receives rewards for being in this grid world. They get a reward at every time step. The reward for just living is some potentially small number. It could be negative, it could be positive. And they get this sort of life reward at every step. And then when certain events happen, like they pick up the gem, this blue thing, then they get a +1. And we'll say, for the sake of this particular example, that they have to pick up the gem, and that picking it up counts as like leaving the grid world, right? So that sort of ends the episode, and then there could be another episode later. Or they can fall into the pit, and if they fall into the pit, the episode's over too, for obvious reasons. So this thing, they start in square 1-1. They can take actions. The actions have these sort of noisy probabilities on them. And the goal is to maximize expected utility. You guys should be pretty tired of hearing me say those words at this point. So how are we going to do that? Right? We're going to maximize the sum of rewards. All right, so this problem is not all that different from a problem that we've seen many times before, and that is deterministic search, right? Remember, in search, we start with a state, we take an action, and then we have a successor function that tells us what the next state is. It's deterministic in search, so we're going to have to change that a little bit, but we know how to do chance nodes now, so we can draw another picture, and we can say, all right, we start in this state, then there's a chance node, and then with some probabilities, we wind up in all of these particular next states, right? So if we go forwards from this state, with some probably high probability, we actually do go forwards, but with some low probability, we slip, we fall to our fiery death. Okay? So now we've added these stochastic actions to our grid world, and it still works as a search problem. It still works as a game tree. All of these other models still work. We now have just a chance node, and there are some probabilities associated with the outcomes. This node at the top is a maximizer node. We're saying we want to maximize our expected utility. The next node is a chance node, and then we would have another action decision, not for this case because we fell into the fire, but for the other two cases, we'd have another max node. Okay? So let's put some math in there. We always love math, right? So this is going to look very similar to the model of search that we saw before. We have a bunch of states. We'll call them S's. We have a bunch of actions. We'll call them A's. Now, instead of a successor function, which told us here's the deterministic next state for a given action and state, we're going to have a transition function, T, which takes in a state, an action, and a next state. The way to think about T is that it's a probability distribution. It says for each state and action, if I'm in that state and I take that action, what's the probability distribution over all the next states that I might find myself in? That's what T is. It's like a successor function, but now it handles these probabilities. It's also sometimes called a model, a world model. I think that tends to confuse things when we're just introducing stuff because the Markov decision process is also a model, but that's a problem model. So we have to keep our our different models separated from each other. But we'll also call these the environment dynamics. So we have an environment, how does it unfold over time? So all these are different names for the same thing. We'll just call that a transition function for now. And there's another function, it's called the reward function. So instead of having a goal like we would in search, now we have a reward function. And instead of reaching a state that satisfies the goal, we're going to maximize expected sum of rewards. We also have a start state. We might have some terminal states. In this case, we have two terminal states. There's this terminal state for we get the gem, and then the simulation ends or something. Like once you pick up the gem, the simulation ends and you're done. Or you fall in the fire and you die, and that also ends the simulation. Okay? So those are terminal states. The episode ends when you hit a terminal state. So one way that we can solve these things is using the tools we already have. We can just do Expectimax search. This thing looked like an Expectimax tree, right? So we can do Expectimax search, and that'll technically work. But we'll see in a little bit that that's not going to be like the most efficient thing to do, and so we'll get a new tool soon. Okay, Markov decision processes. You guys maybe remember this Markov person. We did Markov stuff before. He hasn't aged well. But Markov means that at the current present state, the future does not depend on anything past, in the past of my current state. So the current state is a sufficient statistic for predicting the future. This is the same Markov as in Markov chains, as in hidden Markov models, right? So in Markov chains, we said this is what the Markov chain looks like. It's kind of like a Bayes net. It can go off to infinity. And each of the conditional probability tables looks the same. It says that the conditional probability of xt plus 1 only depends on xt, and that it looks the same no matter which t we start in. Could be t equals 5, could be t equals 6. Same probability distribution. That's the Markov chain. We also talked about hidden Markov models, which have the same underlying Markov chain, but now each one of these states emits an observation, some evidence variable that we can look at, and then we can start to condition our predictions based on that evidence. So this is a different upgrade that we can make, but it also uses this Markov assumption. Now we're talking about adding actions to the picture. So neither of those other two models used actions. Now we're saying we want to add actions. We like actions. We care about making good decisions. And we want to take the actions that will maximize our expected reward. So we got to put rewards in there too. So now we're saying, all right, the core of this is still the same sort of Markov chain thing, but now the states depend not just on what the previous state was, also they depend on what action I took, right? If I'm on that ledge and I jump off the ledge into the fire, that's a different action than if I carefully walk to the side and try and get off the ledge, right? Those are two different actions. So what my next state is depends on my action, and it depends on my current state. And my rewards depend on both of those things as well. They could even depend on what my next state is as well. So we'll see that. And you might be thinking, well, there's a fourth spot in this 2x2 picture. What goes there? Could you do both? And the answer is yes, you could. It would be called a partially observable Markov decision process. Maybe you've heard those words before. I didn't feel like drawing it on the slide because it's a bit more complicated and we're not going to talk about them today. Anyway, maybe we'll have time to talk about them later in the class. Okay, so what do we do with an MDP? Well, it's kind of like when we were in a game tree and we said we didn't know what our opponent's going to do, so we kind of have to think about all the possible states that they might bring us to, right? It's my opponent's turn. I don't know what they're going to do. Maybe they take this chess move. Maybe they take that chess move. I kind of want an answer to any move that they could make. I want a policy. I want a function that maps from states to actions so that I'm prepared no matter what my opponent does for making the next move that I need to make. So a policy was a solution in a game setting. Now we're just thinking about playing a game against the environment. The environment takes moves randomly. These are chance nodes instead of like minimizer nodes. But it's the same principle. So I want a policy that's going to tell me what do I do in every state. And a policy could look like this map here. It says, okay, I'm in this grid world. Here's my policy. If I'm in those states, I go up. If I'm in those states, I go to the right. If I'm in those states, I go to the left. This is a policy. It maps from states to actions. And we want to find an optimal policy. An optimal policy is one that guarantees us the maximum expected utility. Okay, so that's the goal. We want to get one of these policies. Expectimax didn't consider entire policies. Expectimax was just looking, this whole tree starts, we look at all the different branches of this tree. Maybe we have a limited search depth, maybe we don't, maybe we have all the sort of Expectimax tweaks, but the end of the day, what we want out of Expectimax search is what's the first action we should take. Here we're saying, what are all the actions for all the states that I might find myself in? Okay? And the optimal policy depends on the environment that we find ourselves in. So if the rewards are such that, just living gets us a minus 0.01, this is because, I guess we get older. We don't like getting older, so we get a minus 0.01 for just existing. And then it's kind of hard to read, but we get the +1 and the -1 for those two states, just the same as before. Then the optimal policy, and don't worry about how you get this optimal policy. We'll get to there at some point. The optimal policy for this particular environment is to basically take the safe route. So we go around this way and we go to the +1. And if we're here, we actually walk into the wall. So that's kind of weird. Like, notice how in these two states, we're actually walking into the wall. Why are we doing that? Does anyone know? Yeah.
Because that way you don't have a chance of drifting to the -1.
Yeah, because remember, in this weird setup, we have this stochastic outcome for taking an action where 80% of the time we go forwards. If we hit a wall, we don't go anywhere. But if we're in the sort of 20% of the time, with equal probability, we go to the left or to the right. So if we're on this ledge, and we're really trying to avoid falling into our fiery pit, which is over here, right? This is the fire. Well, if we just walk directly into the wall, it kind of feels counterintuitive. It doesn't feel like that's necessarily a smart thing to do. But in this MDP, it actually is a smart thing to do because we're not going to fall to our death. The only thing that can't happen is falling to our death. We might keep walking into the wall for a while. We might get lucky and slip off the wall and, we're home free. We might head up this way. Or we might, get unlucky, but still we don't fall to our death and we go down. But no matter what, we're just we're safe. So this is a very safe action, walking into the wall. And similarly for this bottom corner, walking into the bottom is also going to prevent us from an untimely fiery death. Okay? So here's another MDP. This is a different environment. It has a different living reward. Now it's minus 0.03. And so what you see is, for these same two states, now we don't care so much about the risks associated with just going for it, right? I'm on the ledge, and I think, it's kind of expensive. This minus 0.03 is 3 times as expensive. Living is 3 times as expensive. The cost of living has gone up. Or I guess, yeah, the rewards for living have gone down. Kind of depressing. But now we're all right, based on the new conditions, I think it's better to just go for it, Maybe, this motivated us somehow. So we're just going to, instead of walking into the wall for an unknown amount of time, we're now just going to go for the goal and see what happens. If we have the option of going the safe route, we still will. But if we're on this ledge, notice that we're going to try and take the shortcut. Okay? So there's this trade-off. Should I go around the ledge? No. I think it's still better to go up. All right. What if we increase the living reward some more? So now cost of living just rose again. Now what you notice is that this node changed, right? So this one was going to the left before. Now we've decided, okay, the long way around is no longer advantageous because it costs so much to live that I really just want to get to that diamond already. So we're going to go to the right and hope for the best when it comes to this ledge. And we can crank this up even more. Now notice that the living reward is twice as bad as just dying in the fiery pit. So this is a really bleak existence. But if this is the MDP that you find yourself in, it actually totally makes sense to jump into the pit, right? So depending on what environment you find yourself in, this will change what the optimal policy is. Does that make sense? Yes?
Was it only optimal to survive if the chances of living are, less than dying?
we're just maximizing our expected utility, right? So if expected utility for staying alive is less than the expected utility for jumping into a fiery pit, guess what we're going to do? Yeah. You could argue that this is not a good model of the world. But if we're, if we're in the MDP solving mode, we're just like an agent who gets an MDP. Someone tells us what the MDP is. Our job is to solve that, and solving that for this one is jumping off into the pit. Now, if you're the model designer, you're wearing your other hat, you could say, maybe that's not a good model of the world. Okay? All right. So this is for a grid world. Let me try to convince you that grid worlds are not the only type of MDP. We can also do kind of other types of MDPs. Here we'll think about car racing. Right? What do we want to do when we're car racing? We want to go fast. We want to travel far. So we have three possible states of this car. Basically, it's functioning correctly, and it's cold, or it's warm, or it's overheated and it's busted, and we're never going to drive it again. Okay? Very simplified model of a car. Three states: cool, warm, overheated, and busted. All right? So we can draw this as a graph, and the states of the graph are these three different car states. We have three states: cool, warm, overheated. We have actions. The actions are the colored arrows. So we draw those. We can go fast or we can go slow. And there are some rewards associated with this, right? So going faster, the red arrows get us double the rewards of going slow, except if we overheat, we get a -10 and our car can't run anymore. Okay? So these numbers are like the probabilities associated with the different types of transitions. This says if I'm in the cool state and I go fast, then 50-50, I either get to the warm state or I stay in the cool state. And then if I'm in the warm state and I go slow, then 50-50, I stay in the warm state or I get cool again. Okay, make sense? Then there's a couple of states, like if we're in the warm state and we go fast, 100% probability that we overheat. If I'm in the cool state and I go slow, we definitely stay in the cool state. So these don't all have to be stochastic. Some of them can be deterministic. That's okay. Okay, so this model is as a graph, so we can draw the MDP as a graph. We can also draw it as a table. Some people like tables. I like tables. We can draw this thing as a table too. So for each entry in the table, well, there's an entry for each state, action, next state triple. We're going to call that a transition, SAS prime. And for each SAS prime transition, there's a transition function that tells us what's the probability of seeing that. And then there's a reward function, which tells us what's the reward for seeing that transition. Right? And so these are all the same numbers that we had in this graph. So here's this 0.5. It says when I'm in the cool state and I go fast and I get to the warm state, the probability of that happening is cool state, go fast, warm state, 0.5. So this 0.5 is the same as this 0.5. And what's the reward for doing that? It's this plus 2. That's this plus 2. Okay, so all the numbers in this table correspond to numbers in this graph. Make sense? Table, MDP graph, same sort of thing. We've seen these kind of things before, so it shouldn't be too surprising. All right, so we can think about this as a search tree as well. We can say I start in the cool state, and I can take one of two actions. If I take the slow action, there's a chance node. If I take the fast action, there's a chance node. The environment gets to take its move after I make my move, right? So I take an action, then the environment gets to go, and it tells me with some probabilities, here's what happens. Well, in the case of me going slow, if I'm in the cool state, going slow has one outcome. I stay in the cool state. But if I go fast, 50-50, I might be cool or I might be hot after that. Okay? And that's it. No, there's more in the tree, right? We can keep going. So if we keep going from the cool state, we have the same tree as before. If we keep going from the warm state, we take the slow action and we get back to those same two outcomes, equal probability. But if we go fast from the warm state, we overheat and our car breaks down and it's not great. Okay? And of course, this continues from all of these cool and warm states. We can keep doing this. Take two actions, one leads to a chance node, the other leads to a chance node. We figure out what the probabilities are. We figure out what the next states are. And when we go fast in any of these warm states, we're going to get overheated. Okay? So now we have 3 different ways of modeling this. One is as a graph, one is as a search tree, and one is as a big table. Great? Yeah?
So there's no terminal state?
So there is a terminal state here. This is a terminal state. It's saying, if I ever overheat, that's it. Game over. Simulation ended. Yeah. Okay. So each MDP has this sort of search tree interpretation, and if we make it a proper search tree, what we're doing is we have a maximizer node at state S. S is just a state. It's a state of the world. It could be this state. I mean, I guess we've sort of mixed our examples, right? So we were in the car racing example. Now we're back to the grid world. But S is just a state, any state of our MDP. And then from that state, we have all these actions we could choose. We choose one of those actions. It brings us to a chance node. That's the green thing. And that's saying, I commit to taking this action A. No takebacks. Final answer. I'm going for A. I have to do this. Okay, and then what happens? Can you still hear me? The mic is kind of fussing today. All right, so from that green state, this is the chance node, lots of things could happen, right? We don't know what the next state is going to be after we've hit this chance node. The environment will tell us, after it sort of rolls the dice, what the next state is going to be. And so we get some S prime, but there's different probabilities associated with each of these SAS primes. And so the probability of each S prime conditioned on having locked in our answer for A is given by the transition function. That's this P of S prime given SA. And that's also going to have a reward associated with it, saying, going from this SA, we've already locked in the action, can't change it. Then for each of these S primes I might get to, there's some associated instantaneous reward. And then we get back to a max node. The S prime is another max node. Every time we're at a state, we get to choose our action to maximize reward, so it's a max node. Okay, yes?
Wouldn't this branch infinitely, though? Because you could just go slow and then your rewards stack.
Yeah, wouldn't this branch infinitely, though? Yeah, that's a good point. We will get to that in a couple more slides. Yeah. One more thing I want to mention is that this SA, this green node, we can give that a name too. We call this S a state, and then this you might not have a intuitive understanding of what does this chance node correspond to, but we're going to call that a Q state. This is basically saying I've locked in my answer for what action I'm going to pick, and now I'm just waiting for the environment to respond. This is kind of a non-standard term, but there will be a reason that we call it a Q state, so we'll just call it a Q state. So we go from states to Q states, those are chance nodes, and then the environment responds, and then we go back to states. At every state, we choose the action that maximizes expected utility. Okay? All right, a little bit more recap from last time. We talked about utilities of sequences. We said, if I can get gems along the way, or I can get all the same rewards later, which one do I prefer? And we said, generally, we prefer more rewards to less rewards, and we prefer sooner rewards to later rewards. And the way that we were going to capture this was with this idea of discounting. And discounting basically says, this gem is worth 1 to me now, but if I saw it 1 time step away from now, it's worth gamma. And if I saw it 2 time steps into the future, it's worth gamma squared, right? So it's sort of decaying the value of this gem off into the future. We can imagine going back to our search tree, and we're saying that every time I go from one state through a chance node to another state, that corresponds to needing to discount the future by 1 gamma. Okay? So we go from this state to this state, and we get our instantaneous reward along that action sequence. Then we get our normal 1. Okay? But if we don't get that gem until the next time step, the next state action, next state transition, we get a gamma for the same value, or the same reward. And if it happened 2 time steps into the future, we would call it gamma squared. Okay? So why do we do this? Well, if the rewards end up being infinite, it's going to keep our sums finite. So this is a helpful thing. We'll see that in a second. So imagine that we have a discount factor of 0.5, right? So then that means that if I get this reward at the first time step, I get one reward. We don't discount for the first time step. That's actually very important. Like, a lot of people get this confused. I've gotten this confused before. When do we discount? We discount for in the future. So we're saying future things are worth less to me than current things by gamma. For each time step, it's one gamma discount. So the first time step, if we just, we take one step, we get an R. And that R could be equal to 1, and that we get this one. But for the next time step starts here. Any rewards accumulated in this interval, we get gamma times whatever that reward was. So gamma times 1 would be gamma. And then for the third time step, it would be gamma squared. So this is gamma squared. And so this would be, if we get 1 for the first time step, and gamma is 0.5, then this would be 0.5, and this would be 0.25. Yes? Does that mean that gamma always has to be less than 1? There are other alternatives to using a gamma like this, and those amount to setting gamma equal to 1, but you have to kind of handle these infinite sums somehow. And so there are a couple other ways that we can do it. I'll show you those in a second. Yeah?
How is this different from the grid example where you're just like reducing the total score by, I don't know, like minus 0.01 each time you made a step? Is that any different?
Yeah, how is this different from just taking this living reward for staying alive? Yeah, so the living reward is totally compatible with gamma discounting. It says that if I'm thinking about living rewards at this time step, I'm going to get my minus 0.01 or whatever. If I'm thinking about them at the next time step, they might be the same living rewards. It's minus 0.01, but it's one time step into the future. I don't care about it as much. It's gamma times 0.01 or minus 0.01. Okay, so you can discount living rewards. You can discount sort of like terminal rewards. You can discount whatever you like. Discounting is going to help us, and we'll see why in a second. Okay? Okay, so this is going to solve one of the problems for us that we had last time, which is that if I see a sequence 1, 2, 3, I can do discounting on each of these things, and I get 1 times 1 plus 0.5 times 2 plus 0.25 times 3. This is 1 gamma squared. And if I compare that to 3, 2, 1, I will do 1 times 3, 0.5 times 2, and 0.25 times 1, and that'll be a bigger number. So it's saying if I see the same rewards but in a different order, where I get the big rewards first, I'm going to prefer that because it amounts to higher expected sum of discounted rewards. So now this discounting allows us to trade off between getting big rewards early versus big rewards late. So that's nice. Okay. We also talked about stationary preferences, which said that if I have a preference for this sequence of rewards over that sequence of rewards, then adding some reward to the beginning of both of those sequences doesn't change my preferences. This is actually what gets us the Markov property. So this is like, it's saying that I don't have to worry about any history of rewards that came before these two sequences. My preferences aren't going to change. Okay. So we could do a quiz. I think I might skip this quiz, but this is essentially asking, in this particular grid world, there are these 5 different states. If my actions are go left, or go east, go west, and then when I'm at the 10 or I'm at the 1, those are terminal states, and so I can take the exit action and achieve the 10 or achieve the 1. The quiz is basically what's the optimal policy for these different gammas. We saw that as we change gamma, or as we change the living rewards, or as we change all these different features of the environment, the optimal policy might change. So here this is just like playing around with that. Feel free to take a look at that on your own time, but take my word for it that the optimal policy is going to change as we change gamma. Yeah, in the case where gamma is 1, it doesn't matter how far away from the 10 you are, you're going to want to go towards the 10. In the case where gamma is low, you're going to want to go towards the 1 for some distances. Okay, so someone asked, I think it was you, what happens when we have infinite rewards? Remember, the goal of all this is we want to take the action that maximizes our expected utility. If our expected utility is infinite for two different actions, how do I compare the action that gets me one infinity versus two infinities? These are things that we can't really compare anymore. So when rewards can be accumulated for an infinite amount of time, it gets unclear, like, how do we make action selection decisions? So what are we going to do about this? Well, there's a few things we can do. One is discounting. But another, this is even simpler, is we just say that the episode terminates after some number of steps. We call this a horizon. So this is sometimes the limited horizon MDP case. It says that, like, we have some number of steps left before the end of the episode. We can also do discounting. Discounting works out nice because you might remember from some of your math classes that, like, 1 plus a half plus a quarter plus an eighth, ... adds up to 2. That's finite. So we can have a sum of infinite things, all of which are positive, but if we're discounting in this sort of geometric way, where we multiply by gamma each time, then these things will sum up to a finite number, as long as gamma is less than 1. Another thing that we could do is if we can guarantee that we will always reach an absorbing state, meaning we'll always reach a terminal state somehow, meaning we always know, like, whatever happens, our car is eventually going to break down, then we know that there is no possible sequence that won't terminate, and so there's nothing infinite about this. We can always figure out what the maximum utility is going to be, and then we can compare things and it's okay. So 3 different options. We can have absorbing states, and if we guarantee that we'll always reach an absorbing state, we're good to go. Similarly, if we have a horizon and we say it's a finite horizon, then we always know the episode ends after some number of time steps, or we can use discounting. So for the most part, we'll keep using discounting, but those are the other options. All right, recapping here, we're defining these MDPs. We want a set of states. We want a set of actions. We now have a transition function. This is the probability of each state action, state prime triple. And then we have a reward function that's also defined on these transitions. And we start in some state S0. The goal is to find the policy that maximizes our expected utility. And so we need to be thinking about, like, what is expected utility in this scenario, and how do we use it to get this kind of, like, policy that's the optimal policy. So we'll answer the policy question next time. But for today, we're going to be thinking about all these different optimal quantities, and we're going to start with the values. So we can define the value of a state as being the expected utility for starting in that state and then acting optimally thereafter. And this we're going to call V star. Whenever you see a star on something, it typically means, like, it's the optimal version of that thing. This is also how they named the A star algorithm, for what that's worth. But all these pi stars and Q stars and V stars are like the optimal version of the thing. So that's saying, all right, yeah, from a state S, V star is the expected utility for taking the optimal action from V star, or sorry, from S, and then continuing with the optimal policy thereafter. So we just take an optimal action and we keep making optimal decisions after that. The optimal Q value, Q star of SA, says, first I take action A from state S, and then after the environment goes, I then take all the future action decisions optimally from the S prime and thereafter. Okay, so that's V star and Q star. And then pi star is just a policy that maps from each state to an optimal action. Any optimal action will do. So if there's 2 actions that have the same expected utility, we get to pick. Okay? All right, so here's the grid world from before, and I've drawn, like, the value of the different states on here for some noise and some discount and some living reward. This is the easy case. We have no noise, so our actions always do what they're supposed to do. We have discount equals 1, which means we're not discounting, and the living reward is 0, so we don't even have to think about the living reward. So the only thing that can happen is we walk around in the grid world, We go exactly where we mean to, and at some point we reach a +1 or a -1. So the optimal value from every state is the value of being in that state and taking optimal actions thereafter. And so unsurprisingly, if you have perfect control over your environment, there's no noise, and it doesn't matter how long into the future you need to get this reward, all the states have value 1 except for the terminal states where you have no options. And even the value of the +1 terminal state still has value 1. Everyone see why these are all 1s? Okay. These are the optimal Q values. Instead of the value for the state, there are now 4 values for Q values for those states. And the Q values are the values for that same state, taking each of the possible actions from that state. I could go north, I could go south, I could go east, I could go west. So each one of these states now has 4 different numbers associated with it, and only the ones where we are jumping off to our fiery death get a -1, and the rest of them all get 1s, because even though they might not be the optimal action, we take that action and then we act optimally after that, and our discount being 1 means we don't care how long it takes, we're eventually going to get the 1, so all the rest of the Q values are 1s. So this is not a super interesting case. If we add some noise and we keep the discount 1, it's also not super interesting, because as long as we just don't walk into the death pit, then eventually we'll get our 1s and we'll be okay. But the Q values start to look interesting, right? Because the Q values, when it's noisy, are saying that, okay, well, with some probability, if I go up from this state, I might not go up, right? I might actually go sideways. And so there's some probability of fiery death, there's some probability of remaining in the same state, and then, we can act optimally after that. But so now we have these Q values that are getting lower. And if we decrease the discount factor from 1 to 0.9, now we're saying, okay, I want to get there, but I don't want it to take forever. I care about the expediency of these rewards. I don't have all day. At some point, I got to get to dinner or whatever. So now we care about the value that we're losing for staying in the same state for too long. And so the values sort of decrease the farther away from this 1 we get. We go 0.85, 0.74, 0.64, 0.57, 0.49. And this has to do with 2 things, right? So the discount factor is 0.9, and we're saying this is 0.85. So why are those 2 things different? Well, remember what the value is, right? So the value of this state, this 0.85 state, says I'm going to take the optimal action from this state, and then I'm going to act optimally thereafter. The thereafter part means like I'm gamma discounting that stuff. So I could get at most 0.9, even though I'm going to see this 1 reward, I'm going to get 0.9 for it. But I'm not getting 0.9 for the value of this state, because there is some probability that even if I run for that reward, I might slip, and I might take an extra time step, or I might, slip twice and I might fall into the pit, right? Like acting optimally does not necessarily guarantee me my 1 reward, and it won't be that fast necessarily. So I get 0.85. And for all these other states, it goes sort of decaying backwards until, eventually you get the 0.49. We can do the same thing for Q values. The Q values say the same thing. And so for the optimal action, the Q values are the same as the V values. So you can see 0.64, 0.74, 0.85, 0.64, 0.74, 0.85. So notice on this page, you can see which action gave you the optimal expected utility, and that tells you which action should you pick. When you're looking at V values, those are just the maximum over the Q values. Okay? So are these things making sense? Like, you're seeing where optimal values are coming from, you're seeing where optimal policies are coming from. We've tried it for a few examples. We can try it for more examples. I don't think that will necessarily make the point any clearer. But so, yeah, we can compute the value of a state. And the way that we're going to do that is we're going to start to define some expressions. And we just sort of saw how this is going to go in the previous slide. We're going to say, all right, I don't know how much V star of S is worth. But I can run my Expectimax search, and I know what I'm doing. What am I always trying to do? Maximize expected utility, right? So if I'm looking at these actions, I want to take the maximum over the actions of something. And what is that something? It's the expected utility of the next node. Well, the expected utility of that next node, we have an expression for that. We don't know what it is, but it's Q star of SA. Everyone see how we got there? Great. Let me just clear that up. We'll make it nice. There we go. Now we say, all right, well, I don't know what Q star is. I'm here. But I can just keep running expectimax, right? So this is a chance node. I'm not taking a max anymore. I say Q star. What do I do instead of SA? What do I do on a chance node? I take the expectation. So the expectation over what? Over these guys, right? So there's possible S primes that I could wind up in. S primes. Each one of those has some probability associated with it. So we're going to sum over all the S primes that I could find myself in times the probability of landing in that S prime conditioned on being in this Q state, this SA. And the probability of landing in an S prime conditioned on an SA pair is just given by the transition function. So SAS prime. So the transition function tells me the probability for that SAS prime. And then I have to put in here something. And what is my something? Could be V star, but there's another piece that comes first. Yeah. So first I accumulate some reward for having done this transition, right? So there's this R of SAS prime. And we have to add to that the value of the state we end up in, right? So there's some V star of S prime here. Does that make sense? But what are we forgetting? This V star is one time step into the future. So we actually have to discount it by gamma. Okay? So we can define the value of a Q state by looking at the values of all the next states, weighting by the probabilities of seeing those next states, and adding in the rewards for getting there. Discounting by the value of being, one time step delayed. Okay, so I'll clear this again. We'll write it all nice. There it is again. So now we have this expression for V star in terms of Q star and an expression for Q star in terms of V star. Anyone seeing where this is going? We can put one inside the other. We get an expression for V star in terms of V star. So now we have this recursive definition of value. And this is very simple. It's saying V star is just the maximum over actions. That's this node. That's this maximizer node. Of this expectation, summing over all the next states of the probability of that next state, times some amount of utility. How much utility? Well, it's the immediate reward plus the amount of utility I would get for being in the next state, discounted by it being one time step into the future. So we're going to see this thing a lot of times. At the end of this unit, you'll be able to write this in your sleep. I could knock on your door in the middle of the night and say, "What's the expression for V star?" And you'll be able to tell me, and it'll be great. I'm not going to do that though. Okay, so we could look at our search tree, and we say, why don't we just run expectimax search on this search tree? We can just calculate all these values. I saw how to define things, recursively in the last slide. So, we're good to go here. We just take a max at the first one, then we take an expectation, then we take another max, then we take another expectation. We keep going. The problem, anyone see the problem with this? I think someone already mentioned it, right? This is just an infinitely big tree, right? We could keep taking the actions that don't overheat the vehicle forever, and then we have an infinitely large tree. So there's a few ways that we're going to potentially try and solve this problem, but the problem is that we're doing too much work with expectimax, right? We have this giant tree. We're going to try and avoid doing any of the extra computation that we don't have to do. That's also a recurring theme in this class. We're going to only compute things we have to compute. So if this tree goes on forever, what can we do? Well, we've had trees that go on forever before. We just terminate them early, right? We can limit the search depth. That's one thing that we can do. And so if we limit the search depth, we can compute like time-limited values. This is one strategy. So imagine that this is like a depth 1 tree. This is like the last layer of the tree. We don't think about anything in the future. We say those are the terminal states. If you didn't get a reward by now, you're never getting it. We have some value function associated with that. We'll call this V0. It's saying the value of running for 0 more steps is this value, V0. Then we can compute the value V1 by doing a one-step look ahead in this tree. Now we have a depth 1 tree, right? And we can use the values that we computed in the last step to avoid having to do all the extra work. Whenever we see one of these subtrees and we know that it's like the blue state, the cool state, then we put in the value of the cool state and we don't have to go one step deeper into the tree. And we just build this tree up layer by layer. Each time we're looking one step deeper, but we've already computed the values for all of the shallower trees. So we build this thing up layer by layer, and we compute these time-limited values. So we define V sub k of s to be the optimal value of that state if the game ends in k more time steps. Okay? So k time steps from now, the clock's gonna, reach this. I don't know if I guess it's counting down this way. So k time steps from now, the alarm will go off, our agent will wake up from their simulation, and that's the end of the episode. That's what vk is. Okay? So this is like depth k expectimax search. But then we're going to build it up from the bottom, and that's going to allow us to compute things quickly and not have to do all this extra computation. So here's what that looks like in the grid. We're basically going to have these different states. If we say k equals 0, what are the values of the states? It's not a trick. The answer is actually on the slide. 0. Yeah, right, because it's 0 time steps for rewards to accumulate. All the rewards are 0. If k equals 1, then any rewards we see right now, we get. And any rewards we see ever after that, well, there are none, because k equals 1. We have 1 time step to get rewards. So the only rewards are the ones for these 2 terminal states. Let's increase k. If we're 1 more time step away, then remember, we're saying I'm in state S, and I have 2 time steps left. Sort of fitting, because we actually have 2 minutes left. I have 2 time steps. I'm going to do the optimal thing at each of those time steps, and then I'm going to stop. No more rewards after 2 time steps. Right? So now we get a 0.72. And you might think, well, why isn't that the discount factor? Well, it's not the discount factor because there's noise, and we only get 2 time steps. So if the noise moves us off the right path, then we don't have enough time to get back on the path. Okay, we can keep backing this up. We say 3 time steps. So notice that the value of being next to the goal, next to this +1 state, is like it goes up if you have a 3rd time step, because you can actually you can slip and still get back on track. So as you increase k, you'll start to get value in further and further states away from these rewarding states. And if you increase it more and more, you'll sort of average out the noise. And then if you increase it to 100 iterations, this is like after 100 time steps, what's the value of being in this state if I act optimally for all 100 time steps? And that's these values. So this is like, it kind of converges to the same values that we saw before. That's how we that's how we calculated the values from before. So we're really like building up this cake. Each layer is a limited depth search tree. And then we're adding 1 layer to our search tree, and at each step we're computing sort of deeper into the search. Yeah?
Can you give the attendance code?
Oh, yeah. That's right. Let's see. Where is the attendance code? Hang on. Okay. That's weird. The attendance code seems to have vanished for some reason. So let me take a look. Yeah, the attendance code for today is, I'll just write it on this slide. Yeah, sorry about that. Thanks for reminding me. We'll go back to the beginning, because then you can have so the attendance code for today is Zoom. I happen to remember that one. because of this car racing guy. Oh, you can't see it. Sorry about that. Yeah, here's the code. Zoom, zoom. Yeah, sorry about that. Thanks for reminding me. All right, so we'll go back through a little bit more value iteration, and then we'll look at how do we get optimal policies next time.